As teenagers here in AP Physics at Naperville North, I would say that we probably know a good deal about stress, worrying about getting standardized test scores back or staying up until past midnight to do a final project. But we're not going to talk about that kind of stress. Today, we want to know about stresses in physics. And while stresses are by definition stressful in one sense, hopefully by the end of this video, stresses will be less stressful in the other sense, if you see what I mean. So in most of our physics problems, we pretend we're dealing with ideal, rigid bodies. They don't change shape at all when you push or pull on them. However, in the real world, things generally get deformed at least a bit when they interact with other things. We can use stress to describe how this deformation works. Now, there are 4 basic kinds of stress we're going to deal with: compressive, tensile, shear, and bulk. Let's start with the first 2. Compressive stress is when things are, compressed, and tensile stress is when things are pulled. So, compression and tension are basically 2 sides of the same coin. We define these kinds of stress in the same way we define pressure, force over area. The only real difference between compressive or tensile stress and pressure is that stress is usually for solids and pressure for fluids. To get an idea of what we mean by stress, let's take an example. Say we have a cube. Each edge is 1 meter. We compress it with 7 million newtons of force. The stress is the force over the area it's applied on, 7 million newtons per square meter. Like we said before, stresses make things change shape. This change is called strain. Again, there are 4 types, 1 for each type of stress. For example, tensile or compressive strain is just the fraction of its length an object changes due to tensile or compressive stress in that direction. If that block from before was only 90 centimeters tall after all that compressive stress, we would say that the strain is the change in height over the original height, or 1/10. Strain is a ratio, so it doesn't have any units. Now, obviously, some things change shape much more easily than others. A basketball will squish more than a bowling ball under the same stress. For compression and tension, the ratio of stress to strain is called the elastic modulus, or Young's modulus, and it's entirely a physical property of a material. Something with a high elastic modulus will be harder to squish or stretch. We can take our block again and calculate its elastic modulus, stress over strain. In this case, 70 million newtons per square meter. It's interesting to note that since the elastic modulus is the same for both tension and compression, if you start from the same length, it takes the same amount of force to compress something a certain amount as it does to stretch that same thing the same amount. Not all forces act perpendicularly, though. Friction, for example. So, we have another kind of stress: shear stress. This is where a force is applied parallel to a plane, like putting your hand on a table with shaky legs and pushing sideways with friction. In this case, strain is the ratio of the change in length parallel to the force to the original length perpendicular to the force. Just like the elastic modulus from before, the shear modulus is the ratio of stress to strain, so a high shear modulus means that something is hard to shift. Shear is a bit trickier than tension and compression, so we're going to do another example. On the same 1 by 1 by 1 block as before, say that we pushed the top layer sideways with 20 newtons of frictional force, and that top layer shifted over 5 centimeters. Let's calculate the shear stress and strain and the shear modulus. Stress is easy, force over area. Strain is a bit more complicated, the parallel change in length over the perpendicular original height. Finally, the shear modulus is stress over strain. The last kind of stress is bulk stress. This is when something is being compressed from all sides, so it shrinks, like taking a sponge and squeezing it to make it smaller. In this case, strain is the change in volume over the original volume. And of course, the bulk modulus is the ratio of stress to strain. I bet we can go right to a sample problem on this one. Same cube as before. This time we're going to put it 100 meters underwater. Down here, the water pressure is the same as the bulk stress. Remember that pressure in a fluid is the density of a fluid times gravity times depth. So the bulk stress, 100 meters underwater, is 1,000 kilograms per meter cubed times 10 meters per second times 100 meters. That's 1 million newtons per square meter. Now, if the block is half its original volume at this depth, the bulk strain is the change in volume divided by the original volume, 1/2. And finally, the bulk modulus is stress over strain. Let's do a more interesting problem. Okay, let's go. We have a 0.1 meter tall marble platform with a cross-sectional area of 1/4 meters squared. If the Young's modulus of marble is 50 times 10 to the 9th newtons per square meter, and the platform was compressed 1 micrometer by a box of 2,000 identical physics textbooks, how heavy was each textbook? To solve this, we remember that the elastic modulus is equal to stress over strain. So the elastic modulus of marble is equal to the stress, force over area, over the strain, change in length over original length. We can solve this equation for the force of the books on the table. In total, it's 125,000 newtons. Dividing by the acceleration of gravity 10 meters per second, we can tell that the mass of all of the books is 12,500 kilograms. And then dividing by 2,000 for each book, we can tell that the mass of each book is about 62.5 kilograms, a little more than a house cat. These semi-realistic examples are great, but stresses also show up all over the place in real-world engineering. They can be particularly important in airplanes. I think we can agree that it would be bad for a jet to come apart 30,000 feet above the ground. For example, for a propeller plane in flight, the nose is pulled forward with thrust, while the body is pulled back because of drag. So the bracing wires from tip to tail have to be strong enough under tension, or the plane will be ripped apart. Compressive stress becomes important when the plane lands. The landing gear must be strong enough under compression to keep the plane from collapsing under its own weight. There are shear stresses everywhere things are bolted or riveted together. The wings, for example, are bolted to the fuselage. When a plane is flying, lift on the wings pushes up on the bolts, while gravity on the fuselage pushes down, creating shear stress. If the bolts aren't strong enough under this stress, the wings will fly off the plane. All in all, stresses are pretty darn important to engineers. Anyway, all our calculations are great for helping us figure out how much something will be deformed when you push or pull it, but only up to a point. This whole stress model essentially treats everything as a spring, and just like a spring, it all breaks down if you push or pull too far, like the airplane. Too much stress, and you enter the plastic region, and none of this applies anymore. Eventually, you'll reach a breaking point, and your object will just snap. But that's a whole separate story. As long as we stay in the elastic region, we're golden. No stress. Or rather, there is stress, but you certainly shouldn't stress out over it.